So in last lecture, we uh, have studied about the linear span and the smallest subspace generated by a set. That is the subspace generated by a set. So subspace generated by a set is defined as the smallest subspace containing the subset. In fact, any algebraic object generated by a set means the smallest algebraic object containing that set. So in the previous lecture, we have seen that these two concepts, that is the subspace generated by a set, is the same thing as the linear span of the set. Okay, that is the linear span of a set is nothing but the smallest subspace containing the set. Okay. So before that, let me make a remark. So what is that remark? So remark is like this. That is, an object generated by a set S means the smallest object, algebraic object containing the set. So in particular, the subspace generated by a set S, which is nothing but it is denoted by like this. What is this? This is actually defined the smallest subspace containing S. The smallest subspace containing S. Okay, containing S. And by theorem, already we have seen by the theorem in last lecture, we have seen that the span of S, that is defined as the subspace the set of all linear combination of the set, which is actually a subspace, the subspace is spanned by S, and this is the turns out to be the same thing, the smallest subspace containing the set. So that's why whenever we say that the subspace generated by or the subspace spanned by, both have the same meaning. So the subspace generated by a set or the subspace spanned by a set like this are written like this, span as. So both are the same. Okay, so both the things are same. Okay, so let us turn to another definition. Let's come to the another definition. So what is that? Okay, so I just skip this page here. Okay, fine. So let us write this definition. So when we say that our vector space, whole vector space V is generated by a set, when we say, so the same thing, a subset S, a subset S of a vector space V generates or spans the whole space V, if and only if. In the definition, I am writing if means it is if and only if. Span S is the whole space V. Okay. So whenever we say that the whole space V generated by a set or the any set spans the whole space V, means the subspace generated by the set is whole space V or span of S is V. In this case, we also say that S generates the vector space V. So in this case, we also say that the vectors of S generates or spans the whole space V. So let us look examples. So look at the first example, the null space 0. What about the null space? It is a subspace, of course. The null space 0 is generated by which set? Is generated by which set? Please tell me. Of course, empty set. Because empty set, the smallest subspace containing the empty set is 0, nothing else. Is not it? This is the 0 subspace, that is null space, is the smallest subspace containing the empty set, because empty set has no element. Is not it? So span of phi is by convention and by definition also follows that it is just a 0 vector, because the linear combination can be defined for the vectors for a non-empty set. So empty set, the linear combination cannot be defined. So this is a convention also, that is span phi is 0. Okay. Let us turn out to be the non-trivial example. So this one is a trivial. Okay. So null space 0 is generated by empty set. It is clear to everyone, I think. So let us come to non-trivial example. So in V is suppose R3, the vector space is R3. That is the R3 is a vector space under usual addition and usual scalar multiplication. Let us suppose that the set S is given like this: 1, 0, 0, first vector, 0, 1, 0, second vector, and 0, 0, 1 is third vector. Later on, we will see that these three vectors are of very special in character. Actually, they can generate the whole space, and this concept leads to some new concept called basis of the vector space. Anyway, so these vectors are denoted by E1, E2, E3. Okay, so these three vectors actually generates V. So this set yes generates the whole space V. So how to prove this? Okay, so how to prove this? So meaning is that generates means, let us suppose this is your whole vector space V. Okay, this is your whole vector space V, and this is your small set S. This is your small set S. Let us see. Okay, and the span of S will be some bigger than S, or maybe same, some bigger than S. So this span is a subspace of V, right? This span is a subspace of V, because it can be V or smaller than V. So later on we will see why. Okay, so already we have seen that span S is a subspace of V. So of course it is a subset of V, isn't it? So of course it is a subset of V. So here it is some fine. Yeah, span S like this. Okay, fine. So let us come to this one. Yeah, generates V. So how to prove that this generates V? Meaning is that whatever V you take in the vector space V, you can write as a linear combination of these three vectors. Okay, let me again clarify to you that this set S generates the whole space V. Means if you take any vector V in the vector space V, you can write V as a linear combination of these three vectors. Is not it? That is the meaning. So let us suppose that V is any vector that is 3 tuple x1, x2, x3 in the whole space R3, which is your whole space V. Okay. So let us take, so then V can be written as x1 E1 plus x2 E2 plus x3 E3. Yes or no? Of course yes. Because x1 multiplied by 100 gives you x1 comma 0 comma 0. plus x2 multiplied by e2. So gives you x2 into 0, 0, x2 into 1, x2, and then comma 0. And the last one 0, 0, x3. So if you add up these three, then you will get that x1, x2, x3. That is the vector v. So it is clear that v can be written as a linear combination of these three vectors e1, e2, e3, where x1, x2, x3 are the real numbers. That is the coordinates of the vectors v. So it is clear that this v can be written as a linear combination of vectors in S, that is belongs to span S. Okay. So you see every vector of V belongs to span V, and this implies the whole space V is contained in span of S. But you always know that span of any set S of V is always contained in V, isn't it? This is always, right? This is always holds. Okay. And therefore, what you see? You see that both the things are equal, both the sets are equal. That is, and therefore, this implies that V is equal to span of S. Therefore, S generates the whole vector space. So let me ask you, this example is clear to everyone or not? Here the set S generates V is clear to everyone? Write in your chat box, is clear to everyone or not? Who is not clear? To whom it is not clear? Clear to everyone. Okay, that's good. Let us take another example. Okay. The second example, let us begin with these sets. Okay. So let us begin with this example. In the same vector space, now the question is like this. Suppose the set S is 1, 0, 0. This is the first vector. 1, 1, 0. This is the second vector. And let us take 0, 1, 0. This is the third vector. So question is whether S generates the whole space R3 or not. So actually, yes, then yes does not span R3. And you can see why not. If you see the vector 0, 0, 1, since 0, 0, 1, here the third coordinate is non-zero. And if you look at the vectors of S, then you see that the third coordinate is always 0. So you cannot create non-zero vector by any scalar multiplication to these vectors. That means whatever the linear combination you make from these vectors, you cannot create, you cannot find one at the last coordinate, because the last coordinate for every vector is 0. So you cannot make it 1. Okay, you cannot make it non-zero. So that's why this vector 0, 0, 1 does not belongs to span of S. So there is at least one vector in R3 which does not belongs to this span S, and therefore S does not generates R3, does not span the whole space R3, right? And suppose it is possible for, if it is not clear to you, let us suppose 0, 0, 1 is equal to A times 1, 0, 0 plus B times 1, 1, 0 plus C times 0, 1, 0. Okay. So that's mean if it is possible, suppose 0, 0, 1 can be written as a linear combination of these three vectors, then you can find the real number A, B, C such that this is equal to this. If you compare, then what you will find? You find that the last coordinate 1 in the left side 1, but in the right hand side the last coordinate is 0. The third coordinate is 0. So this is not possible, is not it? This is actually last coordinate. So you see, this is a contradiction. This is a contradiction. Thus, we cannot find scalars ABC such that 0, 0, 1 is a linear combination of vectors u1, u2, u3. Let us call this vector as u1, this as u2, and this as u3. Okay? Let us call this as u2. Fine. So thus, we cannot find scalars A, B, and C such that 0, 0, 1 is a linear combination of vectors u1, u2, u3 in S. Okay. So we are done. So clear to everyone? Is it clear? That is, yes, does not generate the whole space R3, right? Okay. No one is answering. Is it okay? ठीक है, ये एग्जाम्पल की नहीं भाई, समझ में आया कि नहीं? पहले वाले केस में यस जनरेट कर रहा है R3 को, दूसरे केस में ये जो सेट यस है R3 को जनरेट नहीं कर रहा है. ये समझ में आ गया? आगे बढ़े. ओके. Okay, go to the next page. Let me take another example. Similar example. Okay. Let me take another example. Okay, fine. Again, the example is similar to that one. Example is, of course, the vector space is the same. Let us say R3. And the vectors, the question is, actually this is a question. The vectors, which vectors? 1, 1, 0, comma, 1, 1, comma, 0, comma, 1, and 0, 1, 1 generate R3. You need to prove this one. Okay, so how to prove? So let suppose that A1, A2, A3 is any vector. V is this one. Sorry for this. Let V is equal to this one is any vector. Okay. Fine. So let V is any vector, say A1, A2, A3. Okay. So I just put comma here. Is in R3. Is any vector. So then we have to find scalars alpha, beta, gamma such that alpha times 1, 1, 0 plus beta times 1, 0, 1, 1, 0, 1 plus gamma times 0, 1, 1 is equal to A1, A2 and A3. Isn't it? Right. So let us solve this. Here it is alpha. Of course, 1, 1, 0. So if you solve this, then you will get alpha plus beta is equal to A1. Then you get alpha plus gamma is equal to A2. Then you get beta plus gamma is equal to A3. So whether it is possible to find alpha, beta, gamma in terms of A1, A2, A3 or not. So let us see. So we can find. So if you solve this, okay, if you solve this, for example, if you subtract beta and gamma, so you will beta minus gamma, is not it? So beta minus gamma will be A1 minus A2. Okay, and if you take beta minus gamma is this one. Okay, fine. And if you take like this, or we can take gamma. Okay, then alpha plus beta, here alpha, here gamma. Gamma we can replace. Okay, so how to replace this one? Yeah, fine. So beta minus gamma is this one. And where is beta plus? Yeah, beta plus gamma is A3. So let us solve. So beta plus gamma is A3. Then let us solve this. Then you will get 2 beta is A1 minus A2 and then plus A3. Okay. That is, what is beta? Beta is just A1 minus A2 plus A3 divided by 2. If you observe the symmetry, then you will get minus at the place of second. Okay, minus at the place of second. So similarly, if you solve, then you will get another one. That is alpha is equal to, you will get 1 by 2. Okay, A1 plus A2 minus A3. You just observe. And gamma you will get 1 by 2 minus A1 plus A2 plus A3 by 2. Okay. So we can find A, alpha, beta, gamma in terms of A1, A2, A3. Because A1, A2, A3 are real numbers, therefore alpha, beta, gamma are real numbers. So since A1, A2, A3 belongs to R, this implies alpha, beta, gamma are also in R. So these three vectors, three tuples generate R3. Okay, that means every vector of R3 can be expressed as a linear combination of these three vectors. Okay, let us look at another example from polynomial space. So I hope it is clear to everyone. Clear to everyone? Please respond in chat box. Is it okay or not? Let me repeat again. What we did, we just took an element in R3, we took a vector in R3, and we have shown that this vector can be expressed as a linear combination of these three given vectors. Hence, these three vectors generate R3, right? So please respond in chat box. It is clear or not? No one is responding. Everyone is either sleeping or not taking interest in the lecture. No need to meet on Google Meet. Then I will just send on WhatsApp you PDF. Then fine. ठीक है अच्छा ओके अमित अग्रवाल ने लिखा यस सर बाकी लोगों ने अच्छा और अभिषेक ने लिखा ठीक है और भाई और सबको समझ में नहीं आया, या तो कोई है ही नहीं वहां, बस चालू करके छोड़ दिए हो क्या तुम लोग? अच्छा, ठीक है ठीक है, बड़ी अच्छी बात है। कह लो आ गए भाई, 1 2 3 4 5 6, ठीक है। अच्छा, 30 लोगों में से 6 लोगों ने रिस्पॉन्ड किया कि हाँ सर समझ में आया। बाकी लोगों को कोई फर्क नहीं पड़ता, समझ में आया तो ठीक, नहीं समझ में आया तो भी ठीक। अच्छा, फर्क पड़ रहा है लोगों को, थैंक यू। ठीक, अच्छा लगा। Okay, so let us look at another example which is from polynomial space. So we will see just simple examples and we will learn the concept. Then the difficult one you can solve automatically. Okay. Okay, fine. So let us go to the next page. Yeah, go to the next page. Let us take another example from polynomial space. Example is that, let us suppose that the vector space is P2R. So now you know very well what is P2R. That is set of all the polynomials, the vector space of all the polynomials of degree not exceeding 2. That is, zero polynomial is there, linear polynomial is there, quadratic polynomial is there. Okay. So not greater than 2. Fine. So let us write yes. The set yes is 1, x and x square. So here the polynomials are of the type ax square plus bx plus c. So these are the polynomials. If a is non-zero, then it is 2 degree. If a is 0 but b is not 0, then it is 1 degree. If a and b is 0, c is not 0, then it is 0 degree. If a, b, c, both, all the three are 0, that is the 0 polynomial, its degree is -1. Okay. So you have this set of polynomials, which is a vector space of polynomials of degree 2, not exceeding 2. Means it has all the polynomials up to degree 2, which is a vector space. Okay. Now, since any polynomial px in P2R is of the form, what is the form? That is, px is equal to ax square plus bx plus c. Okay, where this a, b, c belongs to R. I'm not saying this is of degree 2 or degree 1 or degree 0 or degree -1. Okay. So it depends on the coefficients. If a is non-zero, it is of degree 2. If a is 0 but b is not 0, it is of degree 1. If a and b both are 0 but c is not 0, it is of degree 0. If a, b, c, all the coefficients are 0, then it is 0 polynomial and it is of degree -1. You know very well. Okay. So whatever the polynomial is in P2R has this type of formation, this type of form. Okay. So this type. And of course, this Px clearly this Px can be written like this: c into 1 plus b into x plus a into x square. That is, 1 is here, you know, this 1 is not it. This 1 is here, this 1, and this x and this x square. So all these three are actually vectors in P2R, right? So S is a subset of P2R. 1 is constant polynomial 1. X is a polynomial of degree 1 having just one term. X square is also a polynomial of having degree 2 and just one term. So all these three are polynomials in P2R. So this is a subset of P2R. Okay. And you see every polynomial Px in P2R can be written as the linear combination of these three vectors. And therefore, what we have proved? We have proved that this Px belong to span of S, right? That means every vector of P2R is contained in span S. Okay? And this implies that Px belong to span S. That means V is contained in span S. Okay. So therefore, automatically span of S, I will not write like this. Okay. And therefore, span of S is nothing but the whole space P2R. Why? Because uh, from here you see that P2R, that is every polynomial of degree less than or equal to 2 is contained in span of the set S. And already you know span S is a subset of P2R. So A is contained in B and B is contained in B. Prove that span S is equal to P2R. Okay? ठीक है. Let us see another example. So today lecture will be finished in examples only. Okay. Okay. So let us go to the another example. Yeah, fine. P2R. Okay. B is just P2R. And what is S? Let us take S is 1 plus x square plus x plus 1. Okay. And let us take I will not call this, let us call this S1. Okay. And let us take S2 is 1 plus x square, 2 plus 2x plus x square, 1 plus x plus 2x square. So the question is, which one will generate B? Either S1 generates B or S2 generates B or both generates B. Okay. So let us see what is going to happen. Okay. Okay, fine. So let us take first S1. In terms of S1, we are going to see whether it generates or not. So suppose, of course, the polynomial is of the type ax square plus bx plus c. So you have to write as a linear combination of these three. So alpha times 1 plus beta times 1 plus x square plus gamma times 1 plus x square. Okay. So let us see if you compare this. So alpha constant term plus beta plus gamma at one place, then plus at another place coefficient of x. So coefficient of x is just gamma. So gamma times x, then plus here coefficient of x square is just beta plus gamma and the x square. So what you see, you just see that gamma x. Okay. If you compare with ax square plus bx plus c, then comparing this, what you get? You get that a is alpha plus beta plus gamma, right? And b is, I'm sorry. This is not. Okay. So yeah, fine. So what is going to happen? That is alpha plus beta plus gamma is equal to constant term c. And then gamma is coefficient of x b. And beta plus gamma is equal to the coefficient of x square, that is a. So already gamma is found. Okay. From here you can see that beta is a minus gamma, that is b. Okay. So beta is found. If alpha beta plus gamma is found as a, so from here you can find that alpha is equal to gamma minus beta plus gamma. I'm sorry. Alpha is equal to c minus C minus, that is yeah, C minus beta plus gamma, is not it? So beta plus gamma is already A. So it is A. So you found that alpha is equal to C minus A is a real number. Gamma is equal to B is a real number. Beta is equal to A minus B is a real number. So it is a definite values of alpha, beta, gamma. So we can find the scalars alpha, beta, gamma so that ax square plus bx plus c can be written as a linear combination of these three vectors, that is 1 plus x square and 1 plus x square. And therefore, what do you see? Directly I am going to write, that is, as we see that, hence this set S1 generates V is equal to P2R, right? That is span of S1 is equal to P2R. So I am leaving up to you. So you decide whether this is a written as linear combination of this set or not. It is up to you. So you just determine whether it is possible to write or not. Okay. So I hope this may be possible or may not be possible. I don't know. Okay. 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 Because you are already going to run out of time, let us see the last example of this lecture. Okay. From the matrix space. Okay. So for S2, you do this. है ना? For S2, this is an exercise for you. Okay. आप अपने से करिए. Okay. So let us come to the matrix space M2R. That is M2 cross 2 matrix. Okay. So what is this? Let us take the set S. The set S is this one. That is 1 1 1 0. Okay. Then it is 1 1 1 0. Okay. Then it is 1 1 1 0. And then it is 0 1 1 1. Okay. So these four are the vectors. So let us call this U1, let us call this U2, let us call this U3, and call this as U4. So these four matrices are the vectors in M2R. M2R means set of all 2 by 2 matrices. So here our vector space V is nothing but M2R, that is set of all 2 plus 2 matrices with real entries. So the question is whether S generates the whole space V or not. So meaning is that any 2 cross 2 matrix with real coefficients can be expressed as a linear combination of U1, U2, U3, U4 or not. So let us verify. So if you take any matrix alpha, beta, gamma and say delta, this is a 2 cross 2 matrix. So we need to find the coefficient A such that 1 1 1 0 plus B, then 1 1 0 1 plus C 1 0 1 1 plus D 0 1 1. So you need to find A, B, C, D so that real number A, B, C, D, so that the value, after putting the value of A, B, C, D, we can find the matrix alpha, beta, gamma, delta. So when you just simplify this, just I will take 2 minutes more. Okay. So just if you add some more pages, yeah, okay. So what do you see? If you see this one, then the first entry is, look at the first entry. That is A11 plus. So in place of gamma, in place of alpha, A into 1 A, B into 1 B, C into 1 C, plus D into 0 means just no part of D. So the contribution of D is not, because D into 0 is just 0. So A plus B plus C is alpha. So A plus B plus, I'm sorry. So A plus B plus C is A plus B plus C is alpha. So I am writing on next page. A plus B plus C is alpha. Similarly, A plus B plus D is beta. Similarly, A plus C plus D is gamma. And B plus C plus D is equal to delta. Right? If you add all these four, okay, then what you get? 3A plus 3B plus 3C plus 3D is equal to alpha plus beta plus gamma. Okay, plus delta. So therefore, A plus B plus C plus D is equal to alpha plus beta plus gamma plus delta by 3. Right? So because you know the remaining three values. So this is A. It is A plus B plus C. So you know the remaining three are already there. That is, if you want to find the value of A, B plus C plus D is already gamma. So just put minus gamma. So minus gamma means minus 3 gamma, so minus 2 gamma. So it will be just value of A I am going to write. So value of A will be alpha plus beta minus 2 gamma plus delta by 3. Okay? You just check that. The value of A is alpha plus beta plus B plus B plus C plus D is delta. I'm sorry, this one is delta. Okay, so let me erase this first. I'm sorry for this. This is actually delta, right? So what you get? Okay, some mistake I made here. Just erase this one. Okay, so the value of A, because B plus C plus D is delta, so minus 2 delta will be there. So A is equal to what you get? You get that. You get that this implies the value of A is equal to alpha plus beta plus gamma minus 2 delta by 3. Similarly, the value of B will be in place of B. So how to find B? B means A plus B, A plus C plus D. So gamma. So minus 2 gamma will be there. So alpha plus beta minus 2 gamma plus delta by 3. Okay. Similarly, the value of C will be C means you need to find where is not C. So here is not C. So minus 2 beta. So A minus 2 beta plus gamma plus delta by 3. And similarly, you can find D. Where is not D? So D in the first equation is not. So minus 2 alpha. So this is minus 2 alpha. And this is not A, this is alpha. Okay. So the value of D is, sorry. So the value of D will be like this. So the value of D is, which one is not here? Yeah, alpha. So minus 2 alpha. So minus 2 alpha plus beta plus gamma plus delta. Then divided by 3. So all these, if alpha, beta, gamma, delta are real number, then A, B, C, D are also real number. And hence, we have proved that this implies that alpha, beta, gamma, delta matrix can be expressed as linear combination of vectors, that is matrices u1, u2, u3 and u4, and therefore every vector of this alpha, beta, gamma, delta belongs to the span of S, and therefore the whole vector space M2 cross 2 over R is contained in span S. But you know that span S is subset of this, and therefore span S is equal to M2 cross 2. Because M2 cross 2R is the bigger space, is the biggest, the whole space. The whole space cannot be smaller than that. So only the chance is equality. So span S is equal. So today up to here, I think everyone clear. So in next lecture, we will see some more examples and some algebra of span of subset.